I don't know how loud the music is, or how loud this anything is. So I'm gonna assume that everything is fine. And I guess we'll start the stream. Because, yes. Okay. Yeah. So nice. Here we go. So yes, we're playing Scrap Mechanic, and we're doing MQ8B. Very nice. So what I want to do in the stream with MQ8B is I want to add some functions and also improve some other functions, and I guess we'll do some debugging to check if how we could improve the speed of this computer, because right now it's not very fast and I would love to get it a bit faster. So I'll remove this glass and yeah. Hopefully I still remember how MQ8B works. I think I do. I'm gonna probably lower the music. I have no idea. Guess like this, maybe? I don't know, just tell someone in chat, just tell me if the music is good. And yes, hello XYZ Gaming, and hello the Burger Box, and hello Cubic, hello myself. So yes, let's begin. What I want to do is I want to change the music is fine, that's great. Okay, so we're going to change the absolute function, which is the absolute function instruction, sorry. And yeah, right now it uses a ripple adder. This is the, I think this is the module that controls the absolute function. And I think, yeah, it's 300, it's about 17 ticks, which is quite slow. And I would love to change that. So I have no idea which instruction it is actually. It's like this one. No. 48 is something else. This one? Oh. Okay, we're a little bit over an overshoot. Yeah, who needs to... Oh, here we go. So yeah, it was instruction number whatever. I don't know. It's this instruction anyway. Yes. So what I want to change in this is because the absolute function, what it does is if the number is negative, it just inverts it, and if the number is positive, it just leaves it be. And we don't really need an adder for that. We could use much simpler thing. I mean, we do need an adder, but it could be a simple, very simple incrementer, I guess you could call it. And we're gonna make an incrementer. So yeah. So we're gonna have an input, and I'm gonna go with a scheme that is I assume the absolute function just sets the input value to be positive. Yeah. So it makes the number positive. If it was minus 10, it will become 10. If it was 10, then it will stay 10. That's exactly that. And so, I probably should explain how the negative numbers in binary work. So suppose we have a number like number 9. So to make it negative, what we need to do is we first need to invert the bits, which would be that. That would be minus 10, I think. And so to make it minus 9, we also need to add 1. And it will become this number. So that will be minus 10 in... minus 9 in binary. And of course, this bit signifies that it's the negative number. So I have a range from minus 128 to 127. So to make a number positive, we're gonna do just that. So we're gonna invert the number. So we're gonna do that with XOR logic. Because we do need to invert it only when it's actually needed to, when it's actually negative. So we're just gonna do that. And gonna connect to all of these gates. So now we can invert a number. Let's add some buttons, just 4 bits, I don't think we need more. And let's, for example, number 9. So it's not a negative number. And to check for if the number is negative, we can just input this bit into here, I think. And here we go, it inverts it. That's not minus 9 actually. That's number much bigger than minus 9. Or I think we need to... No, wait, yeah, this is not minus 9. This is some much bigger number, or I guess smaller. But anyway, so now we need to increment this number. So we need to add 1 to this number. To do that, we need to make kind of half headers, I think. But with... essentially, I'm taking, like, we're gonna make a small counter here that just adds 1. So we'll need a... if the number is negative, then we're gonna add 1 to the first bit. And then we're gonna do that. So we're gonna connect the, our inverted input, or not inverted, if we're gonna deactivate this bit. And we're gonna add 1. And so if this bit is active, like that, then I'm gonna invert it. But that means that we need to ripple that down, right? And so to do that, we need to connect that from here to all of these logic gates. Whoops. Oh. What? Okay. And we're gonna connect to all of these logic gates. And essentially do the same thing like you do with the parallel carry adders. I think that's it. And so we're going to connect these AND gates to here. And you can see that it works. So if we not gonna, if the number is positive, then it will stay positive. And if it's negative, then it will become, well, positive. And it was positive, some big number. Yeah, 120, 100 minus 128 will always be minus 128 is what's the problem with the two thing how's it called? Oh, I forgot how the actual name of this negative number thing. Two's complement, right. So yeah. If we're gonna make, for example, minus 1, which is in binary just all ones, then you can see that it's 1. Gotta eat, I'll be back. Okay. Yeah, it works. Right? Why is this activated? I guess I have not connected it then. Or wait, what? I guess we don't need to invert this bit, we need to take the original input, or... wait. This is not quite right. This should stay like this, but it's not. It doesn't stay like this. Hmm. Oh, right. Oh, I see what the problem is. We're activating the adder. We're actually kind of always doing the ripple here, which we need to disable if quite simply by connecting these gate. Sorry, from this gate to all of these gates. Then we will deactivate the carry, the thing, and then it will become this. Okay, that works. So let's just slap that to our computer. I'm gonna mark where is the input. This is the input. And this is the output. So this is more compact and this is much, much faster. It might be even faster than these carry look ahead adders that I have there. Okay, so what we need to connect is, I think we just need to the A input. So just gonna cut that out of here. Like that, so it would be quicker. And we're gonna place that stuff back. Okay, now let's put our new absolute function to here. I hope I haven't messed up. What? Haven't messed up. I did mess up, because this is the activate bit. Whoops. Shit. I should have looked at this first. I haven't saved this, so I'm just gonna rebuild this part. And I want for everything to stay kind of in the same grid, I don't know. Because I do have like a small order here. And it would be nice to keep everything more or less organized. Although I'm not sure where am I supposed to place the gate that activates. I guess let's place it right here. Yeah, let's just do that. Gonna paint that yellow. And gonna do that. So then we need to connect from from this one to here. And then we need to I think I'm gonna save this module. I'm gonna call it ABC. Okay, well, it's just absolute module. 32 gates instead of however many. There's logic gates in the ripple adder. In a tad bit optimized ripple adder node. Okay, so now what we need to do is we need to connect the accumulator, which is this thing, and we're going to connect it to here. I've forgotten how bad the web of connections there is. It's fine. I'm sure it's fine. Like that. And then it will figure stuff out on its own. Now we need to connect the output to the bus, to the ALU bus, which is this green input. Green gates. And I guess we'll have to program on the MQ8B, because I haven't programmed on MQ8B in a while. I have coded the compiler for it. Oh, we also could test the compiler, because I mean it does output the code, except it doesn't output the blueprint, which would be very convenient. Whatever. I guess I'm gonna just paint the blocks and hope that I have painted everything correctly. which is not very nice. But anyway, let's try to... So this is the instruction which makes our number absolute. So this is 128, right? This is 7 bits. This is 2 to the power of 7. It's 128. And this is 64. 64 plus 4 is 68. So, okay, our absolute instruction is 68. And I think we could add the same delay as on those, maybe less. Why is it white? Haven't I, like, made it green? Weird. Okay. So we're going to load number... Let's load number 0 and subtract some number from it. Let me actually open the instruction set, because I really don't remember which number is which. Oh, sorry, which instruction is which. I don't remember the instructions for MQ8B, because there is too many of them. I think it's 30. Oh, yeah, it was 33. Which is quite convenient. So, 33. And we're gonna subtract... this is 33. Oh, wait, so the instruction was 36, not 48. Okay. So let's subtract number... Well, let's favorite number 9. And let's find an absolute of that number. And let's hold the computer. After that. So we're loading absolutely nothing. We're subtracting 9. And as you can see, we're getting -9, which makes sense. And I can already see that it outputs us number 9. And then, of course, it holds. Very nice. Okay, that works. It's very neat. So I think it would be nice to do one thing, which is to open the chat, because I forgot to do that. But also, I'm not sure. Do I want to make some more interesting function to the add more interesting function to the computer or instruction? Because what I want to add is direct memory access, so we could directly write to the computer's memory, bypassing all of the port stuff. I mean, we still would be working with ports, but we would be able to just directly input data into the computer, which would be much nicer. And also probably fix the ports, or I guess make them a little bit better, because right now we don't really, I don't think they have input. I mean, they don't, sorry, they have input, which is white, indicated by this white, and they have output, which is this green, these green gates. But they don't indicate when the computer actually wrote to them, which would be very convenient, because then the something that is connected to the port would actually know when the computer actually wrote some information to that. So it wouldn't have to like always check if the data is updated. So I'm definitely gonna do that. But first I'm gonna save it, if I haven't wired it to the ground. Okay, I haven't. That's good to know. Oh no, my pedestal is going to be misaligned. That's unfortunate. Did I name it just MQB? Yes, I have. Okay. So we're gonna save this MQB, and actually I'm gonna just place it onto the ground. I don't think it matters too much. And let's work with ports, actually. Haven't worked with those in a while. So port register write and port register read are 112 and 113 instructions. Okay, 112 is just this. And that's the instruction that we need. So let's add 4 of them because we have 4 ports. So port register right. You know what? Let's make something more interesting. So let's load 0. Then we're gonna write port register right. Actually, let's load 1 and then write to port register 0, number 1. And then we're gonna increment it. And so the increment is 34th instruction. So it's this one. So we're gonna increment it. Then we're gonna write to port register 1, this number. And then we're gonna increment it once again. And write data into port register 2. And then we're gonna increment it once more and write data into port register 3, which is the last port. So let's try to execute this. Now I have this slab of wooden concrete here. Very convenient, see? So we're loading it and then we're writing to the port. And I have tested the ports, right? They do work. Right? Yeah, they probably do. So it is actually ridiculously easy to make them work. I'm not sure why I haven't implemented that earlier. That would be convenient. But I, for some reason, haven't. So I guess I'm gonna get rid of those red gates and I'm just gonna paint blocks near them. So yeah, these blocks are needed to they define in which order the ports go. So this is 0th port, this is 1st, this is 2nd, and this is 3rd port. So I'm going to, why is it sliding? I'm going to connect. So I'm going to add this register right here. Guess I'm gonna add it the same way this one. Whoops. Like that. Shit. Whoops, I have a little bit forgotten about the fact that they actually are not connected to freaking anything. That's incredibly unfortunate that I've just... Shit. Okay, I'm gonna make a small window right here. And I'm gonna slap like a block right here, just so it would support it. Because that's ridiculous that it just fell. It fell and couldn't get up. Right, and we're going to put a logic gate right here and right there. And I guess I'm gonna paint them cyan, I think is the color I'm commonly using for this. Or have I used... I don't remember which color have I used in Quantum, actually. I think I used yellow for indicating if there was something written to the port register. But I'm gonna use cyan from now on. Because who needs standards anyway? Standards is a farce. There is no need in those. Anyway, I'm gonna connect to this logic gate. So this first, so 0th, 1st, 2nd, which I accidentally disconnected, and 3rd. Okay, gonna connect to this one. So green here is... What the hell is green? Wait, why are they painted green? Oh, because this is the output. Right, I forgot. I just thought I was a little bit silly and have painted it the incorrect color. I thought that was the input. But no, I have painted everything correctly. I'm just used to seeing XOR gates as the output for the registers, but those are obviously ports which need the activation signal. So yeah, now I need to connect the data input signal right here. I really wish I could kind of connect logic gates in parallel. That would be convenient. But unfortunately I can't. So fifth, sixth, seventh, and eighth. Okay, here we go. I think that's done. And now we have to make those logic gates work. It should be easy because we just have to... Actually, that's ridiculously easy because we can just output these logic gates into here. I guess I'm gonna have a 1 tick delay, but maybe that's for good, because maybe the data wasn't actually written. I mean, it was like a tick delay, maybe it's required. Whatever. Okay, so let's try to... Well, I already have a program which would write to all of the gates, and I have no idea what they output. So I'm gonna have those... I'm gonna output those logic gates right here. And unfortunately I have to run all the way to here to connect those. Which is a tad bit inconvenient. I'm gonna enable fly. Not flew. That would be a little bit faster. Here we go. So that's that. I think that's it. So let's type fly again. And let's execute this in extremely cool function. And yeah, it seems to have worked. I saw it blinked right here. So that works. We increment an output, second one worked. We increment. And it just... Wait. No. Why is it just glowing? That's... Oof. Oh, right. I forgot to connect this logic gate. Where did I connect that? Okay, thank God. Okay, here we go. So, well, it did write, so that's good to know. So I guess it works. Yes, it have worked. Now increment and output, and it works. That's nice. Actually, let's before I do that, let's check if... Yeah, 1, 2, 3, 4. That's nice. So the ports are working, and that's good to know. So time to make ray tracing. I'm joking. Although it could... I think it should be possible to write ray tracing, or at the very least ray matching or something similar. Although ray matching is a subtype, I think. So yeah. Very nice. Okay, now on to DMA, I think. And I'm not exactly sure how do I do that. I'm gonna save it as an actually named this one. Because I don't know if this is a good idea to update the actual version, although I already did, which is not very nice. Okay, so gonna drink some tea and think about how do I implement the DMA. Really hope you didn't hear that. Although if you did, it's fine. ASMR is a good thing. Okay. So we could make interrupts, I think. The problem is, I don't know how to do interrupts. Hmm. How could we do that? And do we use these ports, or do we create another ports? And also, I'm not sure how my memory is connected, because I think it's just hardwired to the to this thing. I have not painted those. Yeah, it's just hardwired directly to the bits of the address of the cache, which is not very nice if you ask me. Because if you're gonna make DMA, then that means that we'll have to introduce a small delay to actually switch off the bus. Although we will interrupt our computer. Yeah, we need an interruption. We need just to interrupt the computer. So yeah, I think I'm gonna well, I will have to add a logic gate somewhere, which will control the interrupt. So we'd be able to interrupt, and well, it will be just DMA access, I guess. So we'll be able to just read and write from the memory, which is very, very cool if you ask me. Because that means we can just, I don't know, write some kind of, I don't know, image, maybe some message, maybe just do something with the memory. I have no idea what. We could do memory, for example. We could write to this address, to last address, which is just 15. So we could write to here some keyboard inputs, maybe. Although, why would we do that if it's probably better to just use bus for that? Do we actually need DMA then? Because images, I mean, I'm not sure what can you do. No, you can do some stuff with images. I don't know, maybe image effects, although again, you can apply them hardware. And that would be much faster and easier. Okay, I'm not sure if I really need DMA then. So I'm not gonna add it for now. Although maybe we do need interrupts, which should be useful, because we could interrupt the computer and tell it to go do something, I don't know. So to do that, we would need so when what I need to do when interrupt happens is I need to obviously hold the computer for a second, jump to some address, and or not, I'm not sure. How does I'm gonna read up on how actually interrupts work. when an interrupt occurs, oops. Okay, when an interrupt occurs, let us assume processor is executing ith instruction. Should be nth, sure. And the program counter will point to the next instruction I plus 1th. When an interrupt occurs, the program value is stored on the process stack, and the program counter is loaded with the address of interrupt service routine. Once the interrupt service routine is completed, the address on the process stack is popped and placed back into the program counter. Now it executes the resume for ith in line. Okay. So yeah, we do need to stop clock. Whoops. We need to stop clock from working. We need to jump somewhere where the we need to first complete the instruction, then we need to hold the clock, push the current address onto the stack, and then we need to do thing. Yes, jump to the interrupt thing address. Interrupt routine address. Do something there, and yeah, it seems plausible. Although, wouldn't that mean that whatever is an accumulator will have to kind of load it again, or do we have to count that when we're calling the interrupt? Like, what are we supposed to do? Do we push the... what? Okay, the address on the stack is popped and placed back into the program counter. Well, it just tells about stack. But what about the accumulator? I mean, it would be completely different if the interrupt did something. Like, we can't account for that, really. Except I guess we could push the stuff which was in the accumulator somewhere too. Yes, computer. Yes, very computer. Hello, sorry. Don't quite remember who you are. But yeah, I'm thinking of how would I implement interrupts. I'm the Devil guy from Discord. Okay, that's nice. Hello, Devil. So yeah, I'm thinking of interrupts for the for my computer, and how do I implement them? Because when the interrupt happens, what we need to do is complete the instruction. We need to push the program counter into somewhere, into stack. But I think we also need to store what's in the accumulator at the time. I'll probably have just one interrupt, I assume. Like, why would you need more than one interrupt? Come on. So that would be very easy to implement. Because we could just complete the instruction, write something to one register, and write program counter to one register, and then the accumulator to another register. I've tried to make a 4-bit computer in Sim and gave up twice. You're all mad lads to handle all that spaghetti. I mean, nah. It's fine. It looks beautiful, isn't it? It's just nice. And it isn't that much of spaghetti. But anyway, I guess I'm gonna do that, what I said I do. So I need 2 registers. One for accumulator, another for program counter. And yeah, I'm probably just gonna spawn them in. That's shift register. I'm not used to that amount of spaghetti. It's fine, you'll get used to it at some point. Hopefully. So we can use this register, or we could use a bit faster register. Because we can. Yeah. Gonna do that. We're gonna use different kind of register. Which would be, I think, suiting, because we don't need to really increment the register. So we could just build it, and it will be fine. So I'm gonna spawn some XOR gates. Almost accidentally shared them. So gonna spawn some XOR gates and some AND gates, and make these one XOR gates. Whoops. And so I'm gonna connect from this one to these ones, and gonna make a loop. Whoop. Is this a little bit faster register? I think. I actually don't know if it's faster. Although I could check, because I do have an oscilloscope. So let's spawn this register and this register. They probably will be the same for... Actually, no, they will be different. I think this one will be one tick faster. Gonna paint it. I'm gonna paint this. And gonna call it drag AB BBD. So BBD is brand batch design, because I stole it, or I guess took it from the brand batch which used these, and I do like those because I think they are faster, which we're gonna test right now. I'm gonna use this oscilloscope, simple oscilloscope, trademark, and I'm going to spawn it right here. So I'm going to make a small stand right here. Connect this one and this one. And we're going to add, I guess, a logic gate to check when this one... Well, actually, we don't really need that. We can just output stuff from here to these white gates. And that's for... yeah. So when the data is actually in the logic gates, then we'll be able to detect it. And I'm going to connect the button to these ones and to this purple gate. And let's try it. Okay. So yeah, this is the lane with the standard logic gate. Sorry, standard register. And as you can see, it's one tick slower. It's one tick behind the actual... behind this one. That means this boy is very fast. Which is very nice. So yeah, we're gonna use this thing. This design, because it's more speedy. And one tick does matter. Because you have one tick, you have another tick, they add up very quickly. And that's just not nice when you're trying to make a fast computer. So, I guess I'm gonna do that, and then I'm gonna wire them somewhere right here, because there's a lot of free space left. Yeah, and yes. So this one will be used for the program counter, which you're gonna just wire right here, like that. You know what we could do? We could cheat a little bit, I think. Oh, no, actually, when we finish the instruction, it should automatically increment the address. Yes. No, that will be... so, yeah, I think that would be easier to just use this one. Because it's an incremented address. So we could immediately write after that. Yeah, I'm gonna... I guess I'm gonna do that. Okay, I'm gonna do this. So we're gonna wire the program counter to this register. Then we're gonna write to it after our instruction is complete. I'm gonna add a XOR. It'd be nice if it was self-wired XOR too, which would control when we actually need to write to those. But anyway, let's connect the accumulator to this register. I'm a little bit curious on how we're gonna put stuff into the register. Wait, what? Okay, it's the third one. So I'm not exactly sure. Because you can see that I have a lot of... Those are all inputs. So... yeah. I could add another input right here, but that would look weird. I guess I could add it right here. I barely have enough space. Actually, I don't have enough space because... it's just not nice. It's a small dilemma. I could make it just so it would just fit, but that wouldn't be nice looking. I can't place the... oops. I can't place another inputs right here because that would block these ones. It's just not nice. I guess I'm gonna place another input right here. 1, 2, 3, 4, 5, 6, 7, 8. So I guess I have more inputs here now. So this one will be blue, and this will be an OR gate. And we can connect it to directly to here. I have no idea where am I connecting. Also, I probably need another input for the program counter, but thankfully there is space for it. So this third one. Fourth one. I'm off to do something, so see ya for now. Okay, bye. See ya. So wire that, wire that, wire that, and wire that. So now what I need to do is I need to from here, so this is the least significant bit. I should probably mark which ones are least significant ones, so I wouldn't forget. And I need to connect it back. Actually, now that I think about it, no, I Yeah, I'm gonna do that way. Because it's nice to have all inputs in kind of the same place. Because if they would be separated, then I would probably forget after some while. And I kind of still want to work on this computer. At least from time to time. And it will be a little bit hard to remember where the inputs for the registers are, if I would split them apart. But that way I do know that this input is connected to this register. Kinda. I can guess. I can check the connections. Kind of. It doesn't matter, it's fine. So let's set another input for this register. Oh, I forgot to paint this one with this color to mark that it's a least significant bit there. Like that. I'm gonna paint that blue and gonna connect the program counter back to itself, but through a register. Yes. Oh, so probably. How long was it? Oh, it was almost 1 hour. Neat. So, okay, now what we're gonna do is we're going to make an actual interrupt, and I'm not exactly sure where to place the port for the interrupt. I guess I'm gonna leave some space for the ports, so there is some space for another port right here, I think. Yeah, there is enough space for another port right here, and some more here, maybe even 2. And I'm gonna leave some space right here for the ports too, because maybe I want a lot of ports, I don't know. So I guess I'm gonna add ports somewhere around here. Actually, let me check. Let me mark where the ports will be then. Because that would be nice to know where the ports might be. So that will go like this, I think. Is it too small? Wait, it's too small. It should be like this. Because we have like 9 bits kind of here. So 4, 4, and 9. This 9. So they go like this. 4, 4, and this is 9. Okay. Great, so like this, and then I'm gonna add some glass. I'll change it later, because I want to add some registers here too, maybe. So this will be 1, 2. Right, that would be nice if this was 3, 4, 5, 6, 7, 8, 9. 10, 11, 12. So I can have 12 ports. You know what? I guess because, well, there is... I don't think I need that many ports. I mean... Well, we're gonna use some kind of port hub for that. Sounds... yes. But yeah, we're gonna use some kind of port... enlarger, I don't know. Port splitter, here we go, here's the name. We're gonna make some kind of port splitter, so we could add more ports. I think that will be more than enough ports, really. I'm gonna add another 2 ports, and then I'm gonna change their order. And it shouldn't change much for the user that I've used previous. Like, that has programs written for it. I doubt that would change much. We just have to connect some ports differently, and that's not that big of an issue. So, right, do I have those ports stored? Yes, I do. Yes, I do. I'm smart. Because I do remember that I have added them at some point. So I'm just gonna quickly throw in one tiny improvement, which is this one. That's the entire improvement. And then we're gonna put those registers into here, and I'm gonna add those blocks so I'd be able to wire those. Like that. And then like that. Great, so I'm gonna put another block right here, just so it wouldn't fall when I remove these blocks right here. And so, I'm gonna now paint the registers, I guess the stuff underneath the registers, with, I'm counting from here? Okay. So 1, 2, 3. This is 4, 5, 6. Here we go. This is how it works now. So now I'll have to disconnect these port registers, these two. Oh, wait, no, I need to disconnect this one and this one. Yes, because this is 1, 2, this is still 1 and 2. But this one will have to be 3, so I'll have to disconnect this one and this one. Okay, that's actually great, because those are 2 registers that are at the top. That's quite nice. So I'm gonna immediately put them back, so I'll be able to connect them. Here we go. And here we go. I'm gonna put this block right here so they wouldn't fall off. And now it's time to connect. Nice. So we of course need more of these. So we added 2 port registers. So we need another bit right here for the decoder. Yeah, I just made the simplest decoder. I think I have connected. Yeah, I have connected to all of those, even though some of them are not used. So I'll need to connect like that. Here we go. And then I need to connect this one. So those 1, 1, 1. So I'll have to connect this one and this one to this one. 1, 2, 1, and 2. Okay, that's, I think, it. Those are AND gates, unfortunately. But whatever. And so now we have to connect the inputs to the inputs of each register. And I could use this tool, because I can. It's just important to not get lost. This one, this one, and this one. Yes, I'm gonna mark those down too. So this one, this one, this one, this one. Place block. Oops. So now we connect this one, this one, this one, and this one. I'm guessing I'm just gonna this one, 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 and this, and that. Here we go. Connected the inputs. Thankfully I connected them in the right mode, because I sometimes can forget in which mode I'm connecting and would connect the inputs like outputs. That's always turns out horribly wrong by not working at all. Now, what I need to do is I need to connect the outputs, and well, I need to connect the control logic too. So 1, 2, and then 3, 4, 5, and 6. Now I have to connect the right signal too, and then I have to connect the outputs, which is easy to do, like that. Where I guess I'm not gonna use the blocks because it's quite simple, I think. Is it simple? Yeah, it's simple. Here we go. That's done. So yeah, I think those are all the port registers connected. Yeah, that's that. That's it. So let's actually try to write something to them. And I assume we're just gonna write just the ones to them. And I'm not gonna bother with the incrementing. So 0, 1, 2, 3, 4, 5. There we go, that's it. And yes, they do all have ones now. I'm not sure in which order they were, but I'm assuming that it was in the correct order. So yeah, that works. The port registers do work. Now I wanted to make interrupts. So let's make them. Before that, I will save this as unnamed 1, 2, 3, 4. And we're gonna make interrupts now. So for the interrupts, we need another port somewhere. And how much space did I have? 2 glass blocks. Just default glass. And then it was this cool looking glass. Just gonna eye it. And yeah. Although actually I need like that. Yeah, I think that's it. So that will be our port for the interrupts. Not quite. It will definitely be bigger than that. But yeah. So what we need for an interrupt is the address where we need to jump. And we need to... So yeah, this is essentially just a port to which we could only write. We can't... I mean, from the outside we could only write. The computer obviously can read from it. So yeah, we're gonna do a simple register right here. And I think we're gonna use brand patch design, I mean BBD. Advertisement of brand patch. Somehow. Oops. So, wait, no. Very yes. Apparently I can't count. Rather unfortunate, but I mean, it happens to the best of us. Forget how to count. So this will be our just... I've connected it the wrong way, I've just noticed. This is the input. We need to connect the output. Thankfully it's an easy fix. Kinda. Here we go. So here we're gonna just have absolutely nothing, and to actually to activate the interrupt, we're just gonna do that. And that literally goes to here. Oh, actually no, before I do that, I will add a T flip-flop, or I don't know, a flip-flop, which we could, yeah, which we could use. Yeah, the XOR logic gate will act as a flip-flop. So XOR, self-aware XOR, because it's -2 blocks. So I guess we're gonna make the... There's not much space for the interrupt circuitry to be here, really. But I'm gonna make it here anyway. So it's rather easy to do, I think. So we need to just have a XOR gate, and then to have a NOR gate, which will invert. So do need to make sure that there is something connected to that AND gate, otherwise it's not gonna work. Right. Well, I could just add another AND gate and then do that. Here we go. So when we activate that logic gate, obviously with one tick, as everything is, we can't activate it once again. And that's exactly what we need. And then we can write into the address. And when this thing is activated, what will happen is our computer will finish the instruction, whatever it's running. And then after this last clock cycle, third of the clock cycle, when it ends, we can do one cool thing called writing data to these registers, and then we can perform a jump instruction. To perform a jump instruction, we need another input. Oof. Yet another input. Yeah, let's fuck it. Let's gonna add more gates. So I'm saving 2 gates for like XOR loops, but I'm not saving gates for the inputs. What is this? Oh, that's for memory. Okay. Well, we can't add any more. Actually, never mind. We can. I can just do a very cool thing called using fand block editor, and just wait. It's relative, so I have to do that. I'm gonna delete it to not accidentally move something important. So gonna paint the input as I do. I have connected it and I have to connect it to the input. And so this input is going to be input for the address from the interrupt. So we have to connect it from here. And which one is the least significant one? It's this one. Gonna paint that. Whoops. So the least significant here. That's nice. Oh no, it won't be parallel then. No. God darn it. It's fine. It's going to be okay. It's going to be fine. So we're gonna mark those. Also, I haven't actually... Is there anyone on the stream? But I haven't asked how's the quality of the stream. It's probably good. It's probably alright. Hopefully. Oh shit, someone's calling me. Hold on. I apologize for the small inconvenience. My mother have called me. But yeah, we're going to continue. So, right. So here we have connected the input from the interrupt register to the program counter, to one of the inputs of the program counter. Should note for myself that these are not completely done, because I need to have a reset signal first and then input, because this is just a normal register that I'm commonly using. Have I enabled mode? Yeah, I have enabled my mic. Okay, so what we're going to do is we're going to do things. So this is activated. When this is activated, when this last signal is done, okay, it sends onto the memory. Oh, we're gonna use this signal actually. Yeah, we're gonna use we're going to use this signal. 100 milli, that's a lot of time. Oh, I also should really fix that timing. And timing of this and the memory timing. Because I'm not sure how much of the computer is the bus waiting and the memory. Because my memory, I think this was... it can't be one tick, it's like 2 ticks. Because first we input the decoder. It takes like 1 tick. Then we actually activate the gates there, activate. Another tick passes. And then the input, sorry, the output gates here activate. So it's 3 ticks. It can't be 1 tick. So I'm assuming that this is like 3 ticks, not 1 tick. Wait. Doesn't make much sense. And this must be less than. I'm gonna set it to 1 tick. Although it's probably 2 ticks because it's like the bus. Let's see how it will turn out. But anyway, we're gonna use this signal from probably here because that does ensure that our instruction is fully complete and we have moved to another address. That ensures it, which is very important when you're doing something like that, when you're doing an interrupt. So when this logic gate is activated, we're going, and this bit right here activates. Then what we're going to do is we're going to write data into the... This is program counter and this is data from the accumulator. Yes. So how do we stop an interrupt? That's my question. Actually, we could... What we could do is we could make it just a flip-flop, but nah, I'm not going to do a flip-flop. That's a stupid idea. Let's use another logic gate, which would specifically disable our interrupt. And obviously we need to disable it only when it's actually activated, which is quite easy. It's just a loop. And here we go. If this is activated, then we can just, well, deactivate it. Or maybe we could, like, add an instruction which would... So it add an instruction which would specifically work on, like, disable exit interrupt or something. Does that exist on the computer? Well, I'm gonna add this button here just to make sure. Then we need to actually... Yeah. Well, anyway, I'm guessing... yeah, I'm gonna have that. So, when we activate the interrupt... What if our computer is already halted? That's my question. What will happen when we activate the interrupt? Will it just do absolutely nothing? I don't think it's a good idea. Well, where would we jump then? To halt? Yeah, let's... If there is no instruction, if the computer is off, then we're just gonna completely ignore any interrupts that will go in. And by ignore, I do mean completely ignore it. So if this is activated, whilst this, if this is activated, then we're gonna care about those two inputs. Oh, wait. I'm gonna have a small thing right here. It's more rational to do that way. Because maybe we want to make this an OR gate. And for example, we want to have multiple interrupts. That would be useful. So yeah, I'm gonna do it that way. Also, I'm using the wrong color. Yeah, I was using the wrong color here and here. Whoops. And here. Guess this kind of greenish yellow, not actual yellow. Okay. So I'm gonna use this color here too, and yes. So if our computer is off, then we're just going to ignore all of that. We're just going to ignore, yeah. so this goes to them, and yeah, when the interrupt is on, I guess we're gonna ignore the interrupt also when we have the instruction like halt. Although, oh, actually that's, yeah, we're gonna do that as some kind of a special case, because when we're halted, we're just gonna, I don't care. So gonna do that as one of the, oh wait, wrong gate. I need to connect that to somewhere right here. So if this is not the halt, then we're gonna do that. Then we're not gonna ignore it. Okay, so let's try, well, we shouldn't be able to call an interrupt right now, and we can't, which is a good thing. But let's actually activate our computer and make it do absolutely nothing. So by absolutely nothing, I mean, for example, just jump to 0. Work. So yeah, right now it's doing absolutely nothing. That's good. That's an infinite loop. That's how easy it is to do in MQ8B. So, in theory, we should be able to activate the interrupt. Actually, let's skip a few addresses. And jump to 1, so we would always have some kind of thing. Yes, so now when we call an interrupt, in theory, what we need to do is we need to stop our clock. And to stop the clock, it's quite easy to do, because we simply have to hold the spot. Although then how do we resume it? Oh, well, to resume it we have to just... yeah, it should be very easy to do that. So when this one is just not activated, so when we don't have an interrupt, it just goes like that. But when we do call an interrupt, then it in theory will finish the instruction. Actually, what if it's at first tick? Then it wouldn't be able to do that. Yeah, right. That would be nice if this one was through one AND gate. Then that would ensure that our instruction have not... Although, wait, if it... Actually, yeah, we can't do that. Because that means that our instruction, well, it wasn't started yet. That means everything will be absolutely fine if we do that. So we call an interrupt. And it still works. What? Is this an OR gate? It's indeed not an OR gate. Because I have connected the wrong gate? Yes, I have connected the wrong gate. I have connected... But wait, no. I have disconnected it. Shoot. Wait, but I have connected something. What the hell have I connected? What is this? Why did I connect that? That's a completely irrelevant thing. Yeah, we need to connect this. Here we go. Yeah, that stopped. Where did it stop? 1. Perfect. Oh, and let's check. Did it right? Yes, it have written stuff into here. That's perfect. And so when an interrupt happens, what we need to do after the computer have finished doing its thing, what we need to do is we need to call an actual signal that would bring everything back to normal. I'm gonna be right back. Yes. Anyway, I'm back. And we're continuing to do something. So what we need to do... Right, I've stopped right here. So I need to first reset the... this thing. And... oh shit. This thing. And then I have to set both of them. Thankfully the sets are both nearby. Wait, that's the wrong ones? Whoops. So this one it controls the program counter. And this one controls the thing. You know? The cool thing. So let's actually try to do that. So in theory it should write... Well, it's at 1 right now, so it shouldn't really do anything. Actually, yeah, it's fine. So we need... I've just realized a small mistake of mine. I don't need to disable the program counter like that. I need to do some other things. So I need to like make it through an OR gate, because we do need to activate it back. It's just that we'll wait some time and then enable it back and send a pulse so it would activate the clock generator. So right, yeah, I think that's that. Right, so our computer have stopped. Now we need to actually perform a jump instruction, which we didn't do. So let's deactivate our thing for now. And so, yeah, when we deactivate, we need to send a pulse. Oh, and I even know which pulse. This thing. This one. And I guess I am gonna add an instruction that would exit from the interrupt by itself. So that means I need an OR gate right here instead of just an AND gate. Like that. And I'll add like dark red so it would indicate. This will be green. And yeah, that's that. I think that's what I need to do. Right. So I activate, right, when we activate the interrupt, what we need to do is we need to, well, wait till the clock stops. Yes, I know exactly what I'm gonna do. Okay, so, when this happens, we also perform a jump. So we write the data into here. We reset it, and then we jump immediately after. Yes. That's exactly what I need. So to write data into the program counter, we need to first obviously reset it, and then we need to do that. And we already have connected the interrupt address, interrupt register into the program counter, so we don't have to do much. So when this happens too. I guess we're gonna make it mark it as which color? This color. So let's reactivate the thing. And so in theory we should jump onto. Let's change the address. Oh, this will be interesting actually, because our computer is stopped right now. So that'll be interesting. Where would it jump? So let's temporarily add. Yeah, I think I'm just gonna add it here. Temporarily add some switches right here. And gonna add a button. And here's the usefulness of OR gates, because we can add buttons from the outside. I'm gonna split them apart a bit, so it would be easier to hit them with the spot gun. Also, shit, it still produces the... I wanted to disable the particles. So let's interrupt onto the 9th address. And let's hope that let's actually reactivate our computer, just to make sure it actually will work when the computer is activated. So here we do a cool calculation. I don't know, we're doing ray tracing currently in this teeny tiny loop. So, and we suddenly went, hey, I want an interrupt. I have no idea, where are we? Yes, we're at address number 9. What do you know? That's... And we have written... Yes, we have... Yes! Hell yeah! That works. That works. Yes, 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 yes. That's perfect. So I'm so happy it works. Now, what do we need to do is we need to figure out how much time does it take to actually jump. So I'm gonna add an oscilloscope, which would. Oh, let's check. Let's actually then add the reset functionality. So when we activate the reset, this in theory should be only one tick. So when we activate the reset, what we do is we obviously reset the interrupt, but we also need to wait till the clock stops. Once again. Shoot. So we can't just activate it. We need to wait till the clock stops, finishes the instruction, and then we need to disable it. That means we need another T flip-flop. So we're gonna place a XOR gate. Very optimized, but anyway. Probably gonna place it through an AND gate, so some smartass couldn't accidentally press it twice for some reason. So only yeah, like that. So when we disable our interrupt, we will bam. Oh right, not yes, right. Let's call an interrupt. So we jumped to the address 9 again. Here we go. So we need this will be inverted. And we're going to check if we can stop it twice. And we can't. That's a good thing. So we need to make sure that our clock has indeed stopped. Yeah, we're gonna connect it like this. Maybe I'll change this up a little bit later. But yeah, anyway, we need to ensure that our clock has stopped. But first we need to start the clock when the interrupt happens. So I don't know how long it takes. So we need an oscilloscope. Kind of making things out of order for some reason. Yeah, I'm gonna connect it like this. Whatever, it's fine. So what we need to check is we need to check how much time it takes from from the clock stopping. Oh, yeah, right, I forgot that we have this thing. So from this thing, wait, I'm gonna just add a few ticks, literally. So gonna connect that, and I'm going to connect that. Whoops, connect that. And we're gonna see how much time in ticks does it take to actually activate this. And I'm gonna use the signal from here. Even though it's not exactly accurate. Doesn't matter, it's fine. Good enough. That's impossible. so it didn't even activate. Is that what I'm getting? Like... Ah! Shoot, I forgot about my own thing. Yeah, if the clock is not even active, we're not going to do anything, we're just gonna... But wait, the clock is not active. Why the hell did it enable? Hey! Bruh. What the f... Oh, the right, hell. Shit. Okay, so what I need to do is I need to, I really don't like this system. Okay, I'm gonna remake it. I really don't like how it works right now. So let's just remake that real quick. So we're gonna synchronize everything with the clock of our computer. Because right now we have everything not synchronized, which is absolutely not nice. So we're gonna make everything. I guess I can't really activate that when the clock... Oh shit, I'm dying. So, I'm not sure. So what do I do? Okay, so I'm going to activate that. That means the interrupt is activated. Okay. Yes. But the thing is, we can activate the thing only when the when we have the clock even active, and it's indicated not only by this. Okay, we're gonna use that as an indicator that our stuff works. Although we'll... no, that's not gonna work. That won't do. Shoot, how do we check that our clock is even working? Okay, I need to add some things to my clock, to how it works. So I need to add a flip-flop instead of this thing. I need to add an actual flip-flop. Almost perfect. So that flip-flop is used so we could activate the clock. Yes. I guess I'm gonna put it right here. So the point of this is that it will control the actual clock. So we can reset it. I don't know why I said it like that. But we can reset it. So this will be a full-on 1-bit register. Through an arcade, of course. So we could write to this thing. Through this thing. And to deactivate it, how do I check when the signal is disabled? I need the opposite of tick generator. I think I can just make it through 2 NOR gates. Yeah, 2 NOR gates. Great, so I need 2 NOR gates. Connect it like that, and then I'm gonna connect it. I guess like this one. So it will oh wow, it becomes messy. So we're gonna invert that, and we'll be able to write to it only when so we need to wait, that's not gonna work, would it? No, it would work. Okay, I see. So what can I do is I can make so it... Yes, I think we don't even need this. So yeah, when this is going to be deactivated, we can just flip it. Assuming it starts off fine. So in theory, right now it should be activated. Like that. But when we deactivate it, the clock will be obviously off. Let's check. And yeah, as you can see, the clock is off. Here we go. The clock. What the fuck is happening? Oh shoot, right. But yeah, I get the point. You get the point. Ah, shit. Okay, I need... Oh, right, I need on the change of signal. Just any change. Are we supposed to be activated right now? No. Go away. So, bam, bam, bam. Let's try tick. Yeah, it doesn't work. That's perfect. Yeah, that's absolutely perfect how it works. Okay. Well, not absolutely, but it's fine, it works. I count it as a success. So now, I'm gonna paint that this color, and I'm gonna paint this color, because it's the clock activation system. Lol. But yeah, we can now enable and disable the clock. Well, kind of. Because we still have to give it like a signal right here. So yeah, this one will be thing. So anyway, when this thing is activated... Wait, what's... Yes, when our clock is working... Not sure if I'll... Yeah, yeah, that will work. So when the clock is activated, right now it's not activated. And so when the clock is activated, we can write stuff to it. And for some reason, jumps a lot. Oh, because I have interrupt activated, actually. That's why. I need to add the reset signal. And I assume through an OR gate, because I will have multiple ways to exit Whoops. Here we go. So yeah, now we are out of the loop. So let's reset the program counter using this button, and let's just enable our infinite loop again. So we could test. Where is this going? So now what we need to do is I wanted to actually check some delay to make sure when we to actually check when we need to write stuff. Wait, why am I have connected the wrong things too. Heck. Okay, I need to connect to the second input, the thing from here. Which I disconnected at some point, what? Okay, So let's try activating the our. Oh wait, before we activate it, we actually need to. So when we activate it, besides that, we also stop the clock, and yes, it will stop. Yes, like that. Yes. Okay. So let's enable that, and let's hope that I haven't messed up anyway. Have we jumped? Yes, we have. And our clock is not working. Our address is... Oh, it's 2. That's nice. So our address is 2. Yeah. That works. So when we exit from the... so now we need to actually reactivate the clock. Oh, now hey, look at that. Would you look at that? It shows me when I have... Oh, I have had something connected to here. Shoot. I should have connected that to here. Right. Let's see. Oh, that's glass. I just ran into the glass. Well, yeah, nothing happened. Oh, and our clock is off. Oh, and we have to reactivate it in a different way. To actually fix it. Yeah, I need to actually... So here we go. Let's activate the thing once again. Bam, interrupt. And which address we were at? 1. And now we have 9 in our program counter. And so 4th tick. So I need a delay of 4 ticks. To make sure that we can actually send the pulse back to the clock, because like we jumped, so we can allow ourselves to do that. And here we'll do just an infinite loop, same as we did before. So 4 ticks, I'm gonna send a signal right here. And the signal, what it will do is it will reactivate the clock once again. And it will also, well, it's really 5 ticks. And it will also, by reactivate the clock, I mean it will do this. And it will also actually send a pulse to start the computer. So let's just disconnect that so it wouldn't... I don't think we need it. Just gonna delete it because it's a lot of blocks. Which is not quite something I want. And so we're going to now bring back our programs. Our very cool programs. So jump to address number uno. And address 9 is, I don't remember which address, but it's some address. Actually, I have to count. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the address, in theory. Just to make sure I'm gonna do that. Here we go. So, right. Let's just run our computer. It will do some cool absolutely nothing. Let's maybe jump to address 2. So here we go. Now let's call an... Actually, let's go to address 0. So it have a lot of space. And here we go to address 5. Oh, sorry, address 9. So yeah, I just want to make sure that everything really works. So we do that, and in theory, we should continue at address number 9, and we should just count up. Oh, wait, I didn't write the address. Here we go. I wrote the address, and let's hope that it works. Well, something extraordinary bad have happened. That's terrible. Oh no. Die. Okay, so for some reason... Oh, probably for the reasons of me being a little bit silly and forgetting that we actually need to wait for the clock. Oh, 4 ticks might be not 4 ticks. Okay, I've just realized the small mistake I've made. Well, we can assume that everything will work. So this logic gate will work only when... Okay, fine, let's go from here. So this will ensure that everything works good. Then we might need to wait like 2 ticks. Yeah, let's wait 2 ticks and let's deactivate the clock. Or I guess restart the computer. Oh god. Oh god. Oh god. Oh no. Oh shit. Fuck. I forgot. No. Go away. How did that happen? I'm back. Welcome. Hello again. So yes, I'm... Okay, the computer works. Thankfully. So currently I'm trying to make an interrupt work. And I think I'm close. For some reason it sends like 1,000 signals and goes into an infinite loop. Which is not pleasant. So let's wait 3 ticks. Okay. So what is the interrupt supposed to do? So, well, from what I understand, the interrupt, when it's being called, we jump to an address, which is included with the interrupt. So we call an interrupt, and it has an address associated with it. And so when an interrupt happens, we halt our clock temporarily, save the program counter into well, it's supposed to be a stack, but in this instance it's just a register in which we're gonna store it. And here I'm also storing an accumulator because I think we need to store it. And so I'm storing the accumulator. And so after we have done that, after we wrote the data from in the program counter to the register and data from the accumulator to also another register, we have to jump to the address which is defined in the interrupt. So yeah, again, when an interrupt happens, when we call an interrupt, we have address associated with it. And so we wait till our instruction finishes, we store the program counter in the accumulator, and then we jump to the address which is defined in our accumulator. I think that's how it works. At least that's how I understood it. So let's try to call an interrupt. Right now we're just run our computer. So what did you make like? What logic you put into it? So to make it work, I've made a which part does what about it? Okay, so this is the blue is the input for when we actually want to call an interrupt. So what it does when we activate it, we write an address right here into this register, and then we wait till our clock halts. We do that by actually no, we stop our clock because that's how it works. So we stop our clock, we disable it, and this little pink gate is actually controlling our clock. So if I will disable it, the clock will just stop working. So we do that, we wait till our our instruction actually finishes, and when it finishes, it sends a pulse right here. This pulse, so like it goes to here, it goes to memory, waits some time, it goes back here through this timer, and back here, and it goes into this block, which actually stores our current program counter and accumulator in these two registers, and then it resets our program counter and then sets a new value to it, which is the value that is in our interrupt thing. So I guess I could show it right now. Hopefully it will work. So right now we're at some address, we call an interrupt, and I can see that it doesn't work. Not quite sure why. So it's supposed to be... Oh! Wait, what? Okay, hold on. Wait, no, I don't want to reset it. Okay, that's extremely weird and extremely bad. Hello? Oh. This is activated constantly. Oh, because this is activated constantly. Oh, shit. Okay. Interesting. That's not what it's supposed to do, by the way. If you couldn't guess it. Oops. Okay, let's stop the clock and let's, I guess, reactivate it. I'm not gonna... I think it could help. Oh, wait. I think you could add a memory bit that flips every time it activates and resets after some time. Yes. On every time it activates and stops it from doing anything. I have when it's on. What? When it activates that mem bit. Well, I have this. What do you mean? This bit controls the clock. If it's disabled, you saw that the clock just stopped working. So what I want to do is I want to first maybe you know, maybe no, I have stopped our clock. Yes, I have stopped our clock, so it's supposed to not work. Okay, I'm gonna try it again. I'm just gonna reset the thing. Where it address that doesn't even exist. That's nice. Oh, and I forgot to disable the thing. Got to disable the interrupt. Okay. Hold on. So when an interrupt is called, what we need to do is we need to wait. This is supposed to have one tick instead I have like few more ticks. Which is absolutely not what I want. Oh, wait. No, what? There is only two things that connect to it. So it's this part, and then add a tick generator. Everything here uses one tick, so I don't need a tick generator. Like the clock is one tick, the interrupt is one tick, everything is one tick. I don't think I need a tick generator. But we'll see, maybe I'm mistaken. But anyway, let's just start the clock and maybe add something. Maybe something broke or is generating a signal that is too long. It could be. It could be. Well, it is. Stuff, cause it's not working correctly. I don't know if there is because I can see that it sends still one tick. It's not long, it's one tick, I can see that. But it sends a lot of it, like it causes a loop somewhere. Which is not exactly what I want, and it happens. So if I'll delete that, if I'm not gonna use that clock, everything, it will jump. Oh, I see. So when we activate the jump, we still send the pulse right here. I haven't, that's why, right, I forgot. That's why I have this bit right here. That's what I need. That's why it loops. So after we actually have jumped, we have this timer right here. And yes, when we have finished our jump, we go to here, we wait like maybe 3 ticks like this. It's 2, but the timer adds 1 tick, so it's 3. We enable this, we flip this bit, and well, we invert it, making this loop not possible, so it will disable, it won't work. And let's just try it, and in theory it shouldn't loop. And it doesn't. And it does not loop. And it have indeed jumped. Okay, yes, that was the problem. So now what we need to do is we need to... You unbroke it. Yes. Thanks. So we have that done. What we do after that is we... Well, I should have also sent the signal back here, which would make it start again. So it would start a computer? Yes. And then after the interrupt finishes... Oh shoot, when the interrupt finishes, we need to also wait till the instruction finishes. I think, which is a little bit painful. Also, the deactivation should deactivate that too. That should be easy to do. Can I also use an... Oh. Like that. So, let's disable that. Oh, and yeah, when we disable that, we also need to jump back. And right now I don't have anything. So we need to do what? Okay, let's just do that. So, yeah, our clock still is not on. Although it should be, because... Oh, wait, no, it shouldn't. Okay. Ah, right. Oh, okay. So let's run it again. And let's enable this again. So, in theory, what it should do, what should happen is it will store all of that good stuff, what's in the accumulator. Let's actually write something into the accumulator. Like this number, 5. So in theory it should store what's in the accumulator right here. And store the program counter. I'm sure it will do that. Then jump to the interrupt address 9. And then it should start the clock once again. Huh? Shit! That's incorrect. Wait, why does it enable and disable it? Oh, shoot. Okay, I guess I haven't waited long enough. At least it's not the same bug. Well, it is the same bug, but at least it doesn't destroy itself. Except it does stop a clock. Well, we are at this address. Let's jump back. I really need to bring this button into the... Does it have reset all button? No. It's easy to do because I have that gate and that gate, but I don't have the reset all button because every computer needs one. The reset all button is just putting it on the left, really. So let's activate it. Whoops. I forgot to make the... Oh, I guess that... Oh, I guess that works. Yeah, that's fine. Wait, what? Did it start with... Okay, so this thing is having definitely an issue. Yeah, let's just do that. I'm sure nothing goes wrong. So let's try it once again, and let's maybe just set it to 4 ticks, and let's hope that it doesn't double tick. Let's actually check. So let's actually think a bit. So this thing activates once, sends a pulse right here. This thing activates the switch, the flip-flop, inverts it, and goes back. And in theory, it should just stop the computer. Oh, wait, hold on. It sends a tick. Ah, so, okay, I see. We need to reset the signal. Wait, no. the clock is already off, so it shouldn't have any signal. Dang it, okay. Okay, let's just... God darn it. Oh, didn't die. That's a good thing. Oh god, wait. Yeah, I definitely need to bring that button somewhere. Or actually I could... why can't I just do that? I'm just realizing. Okay, so this is reset. Let's just activate the clock once again. Let's call an I'm not sure what's happening. Why does it double send? So it disables the clock. And when it disables the clock... I don't know, let's just try waiting long enough. That must be long enough. Half a freaking second. Oh. What the f... So that means it sends the signal right here 2 times for some reason. Ah! Right, I've said that... Oh god, okay. I've realized my small teeny tiny issue. That's even more of an issue. But anyway, I've realized the small mistake that I've made. Spaghetti moment. Yes, it is quite a spaghetti, and that's not nice. Okay. Apparently it still works, and even amazing. That's lucky moment that it just works like that. But anyway, I've just figured out, so let's bring that back to 2 ticks as I wanted it to be. And let's hope that it just works. At least your spaghetti is organized, kind of. Okay. It's less of an issue. Because it just doesn't even activate it. Well, yeah, obviously, because I don't send any signal. Okay, I think I could fix it differently. I could add another logic gate, and I shouldn't really need to do that in the first place, but I'm going to do that. Because smart. And this one will be controlled by this logic gate. Wait, it is already controlled by the free... Oh. Wait. So... Ah. Okay, I need to activate this just immediately after... Okay, I see. So I need to activate this thing immediately, not just at this moment, but right here, and delete this. Then it will work. So, okay, I don't need another logic gate, thankfully. It will become activated, so I'm gonna just do that so it wouldn't destroy itself. So I can do that, and so it sends a signal, it pulses right here after the instruction is finished. This signal goes to here, so it immediately stops working. It immediately disables that whole thing, whole contraption, and also sends a signal right here, which after 2 ticks, or actually 3 ticks, I guess, it sends a signal to activate the clock again. And actually, I think we don't even need to wait that long. So, we're just gonna make 1 tick. And let's hope that it just works, okay? It just works. We're at the correct address, our computer is running, let's do that. And yes, it worked. Hell yeah. Okay, that's great. It have worked. Now it does the thing. So it should have, well, yeah, it saved the 2. We were at 2 address, at address number 2, and we had a 5 written on our accumulator. Same as we do here. But let's just for fun add an increment instruction, which is some random instruction, which the number of which I don't remember. But the number is 34. It's this number. So it will just increment our accumulator, just to really make sure that, yeah, even it doesn't matter if it overflows, it's a good check. So now, when we press the red button, what we need to do is we obviously need to reset that, and we also reset that. We need to wait till the instruction finishes. If this is a flip... no. So how do we do that? So do we need to reset? Yeah, I think we need to. So we reset that flip-flop. Let me just... It's that bit annoying how it looks like. Just gonna... Wow, thanks for fucking up my computer. But I should have expected that. Hopefully that still is a XOR gate, because I have no idea how font works. Probably should have checked it before I did that. But there is no comeback. Okay, let's actually reset then. So it have halted my computer. So let's do that. Let's actually check that everything works again. It should in theory work. And it doesn't, because font is an ass and makes the self-aware XOR gate just a XOR gate. Freaking incredible. Okay, I think I remember where it goes. Yes, like that, and then like that. And then we also connect this gate to there. Like that. And I'm gonna paint that. And yeah. Let's so everything is whoops. Fine. Let's make a jump. And as you can see, it works. Now what we need to do, when the reset happens, we also need to disable the things, mainly the clock. Wait till the instruction finishes. Yes. Wait till the instruction finishes. That's quite easy to do, I think. So we just stop the clock. We wait till the instruction finishes, which is because we have reset it. Because we have reset this part. We need a separate reset, I think. Okay, I have an idea. What if we would add another flip-flop? I think that's a good idea. That's a perfect idea. Let's just add another one. So, yes, I do need this thing. And let's make a loop. Trust me, I'm an engineer. I know what I'm doing. Not really. So anyway, like that, and so I need another logic gate that is similar to this one, but not quite. U is engineer. Yes. I'm gonna paint that a little bit that color. I trust you to have more brain cells than me. Maybe. Who knows, maybe you're mistaken about yourself. So anyway, we're going to... let's just... so we will enable that one too. Or wait. Do we reset or enable this one? I think we should enable this one. So when we enable this one, that means that this thing is activated. And when this thing is activated, we know that our instruction is finished. Therefore we can do what? Oh, we could jump back. That means we could do... I think we need to do this. This one is the one that I've made to... Where does it go? Reset. Well, that doesn't tell me much. I have no clue where it goes. Oh. Oh yeah, it goes right here. Okay. So yeah, when this happens, we're gonna... I'm gonna reset. We're gonna enable this flip-flop. When this flip-flop is enabled, actually I just want to... Probably I shouldn't connect it directly to here. I should connect it from here. Because that would ensure that we couldn't like click here 2 times and it would do some bad stuff. So okay, we reset, and in theory we should just wait till the instruction finishes and we should just jump. Oh, and I forgot to enable the clock, but did we commit a jump? No, we didn't. Shoot. That's bad. Oh, because... Wait, what? Have I connected those to the correct gates? Wait, what? Which one is... Okay, I certainly have connected those to the wrong... Or wait, no. No, I have connected them to right gates, it just didn't jump? It didn't enable. Okay, wait, let's just reset our computer for a sec. So we do that, super smart calculation. So we do that, it still works, which is good. So we're at 9, and then when we're do that, we should activate this one. Oh wait, no, what am I doing? Right, we need to actually activate it, not deactivate it. So yes, we activate it by resetting it. By resetting these two. We activate this one. When this one is activated, we go to here. Wait, when the instruction is finished, it will go, signal will come out of here. We'll do that. We'll write the data back into the registers where they're supposed to be. And so, then it should enable it should disable itself once again. Probably after some, just like one tick, well, 2 ticks. After here, it will wait a whole 1 tick and reset itself and also start the clock. Because in theory, the clock should be disabled. We have disabled it before, right? When the thing. Wait, when did we reset the clock? Okay, this goes to the clock. Yeah, this one goes to the clock. Okay. So let's reset it. It shouldn't loop, right? It have looped. Oh, although it have looped right here. Oh, because we didn't connect anything to there, but have it? No, it haven't even started the computer. That's shit. That's incredibly unfortunate. Yeah, but I forgot to reset for this one to even connect it. But I don't think we even need one. Okay, fine. I'm gonna have one block right here, even though I kind of want to move it. I'm just not gonna use this tool because it messes up with the self-wire store part. Okay, so restart our computer once again. Call an interrupt once again. This time it just died. Right, that's absolutely horrible. That it doesn't work every time. That's very, very bad. Okay. Wait, what? How did that happen? So now it didn't... Right? It didn't even jump. Well, I have connected those to completely different... This is... like, what? Okay, I'm extremely confused now. It shouldn't have done that. So we ran the computer. It's... Whoops, it's activated, what? Oh, that's incredible. Why does it not work? Why does it not work? Oh shoot. Yeah, I probably need to also make sure that we... Well, in normally this really shouldn't happen. Also, oh right, I need to implement the halt instruction. I've just realized. And I'll implement it by doing that. So right. Oh, what the hell? Wait, what in the world is happening? How is that even possible? We should activate the clock. So let's disable that for now. So we run our computer. It's running the previous instruction. We call an interrupt. Oh, I'm so tired at this point with working on the interrupt. It worked now. Okay, I really am worried about that. That's very bad that it's inconsistent. That's extremely bad. I hate that. Because when it's inconsistent, that means that, well, it's inconsistent, it's bad. Okay, well, let's just try to do that. Oh? 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 Did it? Hi, I think it worked. I think it worked. At least it really seems like it. And this thing did reset. That's good. Yes. And we should be able to implement the function that which would, sorry, the instruction which will exit out of the interrupt by itself. Let's try to call an interrupt again. And it works. Let's just, hey, I want to exit from the interrupt. It worked. Why was it inconsistent then? Okay, so I'm gonna work at this part. So right now both of these rely on the fact that just only the clock. Wait, no, what? What do they rely on? Oh, they both rely on the fact that the previous rely on... Okay, they both rely on the flip-flops, which is not good, because we have instructions. Wait, there is something else coming into the... What is coming into this thing? Oh, right. I've kind of forgotten what this does. That's that bit problematic, but it's fine, it's fine. It's just impossible now to debug because I forgot what it does. Wow, incredible. Anyway, it will work fine. But what I need to do is I need to actually make sure that our instruction... So what... Yeah, this ensures that our computer will be able to even call an interrupt. We need to make sure that our instruction is not hold instruction though. And by the way, this should... Wait, why am I connecting everything to the flip-flop? It's kind of unsafe because I do have a reset right here. Why have I connected everything to that? Shoot. I could have done everything. That would have been safer if I would do that instead. Slower but safer. Because it's not just gonna go insane. Just disable the clock. Dang it. Okay. Let's rewire everything. But it seems to be that... So when this one is activated, we don't really need to do that. We need to connect to this logic gate. Wait, have I? Yeah, I have grabbed the correct logic gate. So I need to connect it to here because we need to reset it. Then this thing, I think it sets the signal. Okay, it doesn't reset it. Let's just check once again. Okay, it didn't work this time. Oh, because I didn't press it. Because it cannot work, because I have done a little bit incorrect. I need to check if there is no hold instruction, not if there is instruction. That was my problem. Yes. That works. And so... now. This instruction... Okay, it enables the thing. Do I have any ones that disable it? That are going into here? Well, there is one logic gate that goes into there. And I have to somehow track it down. It was this one. And I'm not sure what it does. So when we stop, I guess it resumes it? Does it? Okay, let's connect an oscilloscope to really check, because I'm not sure what it does. Kind of forgotten what's the point of it is. It's bad. Wait too. Okay, here we go. And so when this is activated, we're going to track. Don't really need to track that. We could just track the state of our thingy thing. Okay. I see. So yeah, this thing does reset it. Because after I pressed it, it became 0 immediately. So yeah, I need to connect it to this one. For just some slight safety. Although it might break the computer, I'm not sure. Let's test it once again. So we call. It works exactly like it's supposed to. And let's call back. Okay, it works. It works. It works. It works. It works. So we do absolutely nothing. And here. Boom, 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 boom. Oh, wait. Wait. Haven't we have... what? Oh, we have called an interrupt at the address 9. Right, that's why it did it. Or wait, what? No, it what? What? Wait, what the frick? So let's call the... So we're doing that currently. So let's call n. Okay, it worked this time. I'm probably gonna put the a tiny 4 bits from my counter to here, so I would be able to understand where are we even. As that would be much easier. So right now it's fine, it's going okay. Oh, yeah. That's great that it does absolutely nothing. That's exactly what I want. We call, and it jumps. We call, and it jumps. Call. Oh! Wait, what? Oh, that's bad. What? Okay, well, at least the clock wasn't broken, but... Wait, what? What? Why is it... overclocks itself for some reason. So we call an interrupt. And it does absolutely nothing. Let's increase the timing. I think that might be the issue that I'm having right now. Let's increase it to 3 ticks. I'm surprised that it's in the same... Yeah, it doesn't double signal. Doesn't pulse. Now it did double pulse for some reason. Why the hell? Okay, let's wait a tad bit more. Let's wait 5 ticks. I'm afraid that's the problem. Oh. God damn it! What are you doing? Why is he doing that? Oh gosh, this system is horrible. I'm not gonna release that computer. I'm not gonna update it as this computer for sure. Because it works horribly. So, at the newest version of the computer, I'm not gonna release it with this function. Because it's absolutely horrible. You want to see even worse unfinished computer? Yeah, I guess you could send me a link in the either Discord or YouTube chat. Okay, but yeah, at the end release, I'm not gonna have this feature. I'm just gonna... Really, I'm gonna cut it out right now because that's bad. That's very bad. It's unstable, kind of works, but definitely not worth it. Interrupts suck. Steam friends list. I have you in friends list. Maybe? Sorry, I have, Do you have me in friends list? I don't think you do. Send me the code, or I guess I could. I have. Oh wait, you are. Okay, well, I'm gonna for now continue deleting. I'll end. Okay. I'm not sure why am I completely removing it from the computer, but I do. Okay, so this feature was a mistake. I'm gonna make sure that the computer even works after I've messed with it so much. Because I have added some features that are nice, but I just want to make sure that it works after. So I'm gonna delete those buttons from here. Oops. Okay, I think let's try the, for example, jump. Just infinite jump. By the way, it's my Steam. Well, you probably can't see that actually. I probably should disable that. Okay, so... Oh, no, no, no. Hold on. I'll be right back. Okay, I think I'm back. So right, might actually finish this stream because I am a little bit tired and probably should eat something. So I'm gonna wait while Medic sends me stuff, and we're gonna look at his build, and I guess we'll wrap up the stream on that. And I'm gonna wanted to check the computer if it works after all of the torture that I have endured. It certainly doesn't. Oh right, I should delete these spots. So yeah, in an observable future there probably won't be interrupts, or maybe I'll add them, but I don't know. Yeah, probably will make a stream about it. So yeah. For now I'm gonna delete all of that. There we go. And the medic have sent me his abomination. Very nice. I really shouldn't play this out. Hold on, I'm gonna do that real quick. So okay, I think that's done. I think I've removed the remains of the interrupt function. Let's try to... Okay, it does seem to work and does seem to function, and let's add the instruction that doesn't exist. Well, the punch card reader should have a switch to turn it on. Okay. Oh. Ah, right. Probably should do that. Also, I've realized if the instruction is unknown, the computer will bug out. But that's the problem of the user. If the user is dummy, then it's his deal. Okay, well, yeah. So expect it not to function. I'm not even sure if it works properly after being put on the lift. I didn't finish it, so expect it not to function. Also, the punch card reader tends to jam. Interesting. I'll certainly check that out. You can update it by placing a block. We'll see. I'm just trying to... right, I do need to have the instruction return something. So I do need a return signal. Like that. And also should paint this black. Certainly an interesting way to halt. Okay, you know what? Maybe just having that is good. Oh wait, I think I've realized that my... Okay, I'm gonna check. So this should be... Oh, and it's on. Shoot. Gonna disable it. It's still on. Although it does turn off when I... Actually, yeah, I'm gonna leave it like that, because I can't turn off the button right here. Yeah, I'm gonna leave it as such. To be that. I guess the computer is done. I'm not gonna upload it just yet, because I want to debug it after the stream, and debugging is extremely boring, so I'm not gonna bother anyone to do that. So now, let's load the abomination. That's that looks pretty interesting. I probably should. Oh right, advanced physics. I'm used to non-existent physics in scrap mechanic. So okay, so this is the build that Medic have sent me to check it out. That certainly looks interesting. It's disgusting. It's fine. There's a button. That's probably something. Some debugging, I'm assuming. It was just one big improvisation. It can't even do maths. It's just a memory that reads from punch cards. Okay, so I'm assuming this is RAM. That's an interesting way to implement RAM. Just spawn the card. Okay, oh right, you have sent me the card too. I saw some horns, so I'm assuming it generates some sound, so I'm gonna disable music for now. Insert it and switch the... So... Oh? How do I insert it? Get it in with the hammer. Okay, that's not... Wait, can I just kind of... Can I just do that? Oh? Yeah, I can. It's fine. Perfect. I assume nothing broke, and so... So till which point am I supposed to load it? There is a switch near the engines. Right, where are the engines? Right here. That's the switch, I'm assuming. Or that's the switch. Oh. Well, probably should kind of push it a tad bit because it's a little bit having a stuck. Oh, did it? Here we go. Yeah, you probably should have used less friction blocks because wood is very well, it did something. Update it with placing a block if it does. Feels like a bomb right there. So well, as you said, it doesn't really do much. The program just saves 1 to address 1, 2 to address 2, etc. It didn't save anything to address 1. Oh. Okay, well, I assume the program is... amazing. Have a check at the punch card. Oh, I see, yeah. And these ones too. No. A nuclear bomb going off. Warning. No, it's going. It's going. Not quite. I don't think that helped. Oh no. Oh no. Oh shit. Oh no. Oh, it's rerunning the program. Because I accidentally did an oops. Ah, it's fine, it will re-execute it. Well, that's an interesting... Oh, hey, look, it wrote 1 now. I got some more punch if you want to suffer with it more. I mean, it's not much of a suffering, it's just... it does not much. Also... the RAM is a little bit not supposed to work, I'm assuming. Because it kind of just... doesn't do the right thing. Because it just empties the memory now. It did write the 1 in the first address though. Why is there a cube right here? I'm curious. Like, why are the sensors and the cube right there? What function are they doing? So, oh, to activate the memory. That's very mechanical computer, I've got to say that. Sensors are for reading. Yeah, I see. They're connected to the memory below. And are you using like a... swear, are you comparing the address on here with the address on there? Or seems like it. It just has some poorly done failsafes to make it safe on the correct address. Okay, I see. The first one just waited for printhead to move. Whoops. Well, yeah, it's very hard to pull out the card. But it's fine. That's cause yeah, I got another one. What does that do? What does another card do? I'm gonna reset the memory like that. What does what do? What does the another program card do? You said that you have another one. Oh no, it just clears memory. Okay. Oh yeah, okay, that makes sense. Well, this is... I wouldn't really call it a computer because it's not... It can't do math, so it's... by definition shouldn't be a computer. It's... interesting. It was an attempt. Yes, it was definitely an attempt at computer. It's fine. It's okay. It does something. The point is, it does something. That's the most important thing. Hope you can learn from my mistakes. Well, I might have had those mistakes and just have learned from myself already, but cause I can't. Well, I mean, I guess I could teach how to make computers in Scrap Mechanic. It's not hard. Because I can show you my very, very first computer. Do I even have it? Yes, I do. It's using Russian characters. That's why the Scrap Mechanic just doesn't work. And this is my very, very first quote-unquote computer. But it's not Turing complete, so it's not a computer. And it can do something. It does have this memory. But this memory is a program memory. So yeah, you have to write the instructions into here. And then store them using this button. And then change the address using these things. What does that do? Oh, that, I guess that executes the code. This resets the entire memory, which is a cool function for the program memory. But yeah, there is no it's not Turing complete because it doesn't have jump instructions. Any kind of, it doesn't have conditions, any conditions at all. So unfortunately you can't really do much. It's kind of a calculator though, because you can add two numbers together, you can subtract them together. Sorry, you can just subtract them. You subtract A from B, and the result gets is written into C, and then you can from C move to A or to B, and I think from B to A and vice versa. And so yeah, I also DM'd you the first one. Oh, the ugly UI memory. Gonna check that. Cause I don't know. But yeah, it's a simple computer. The problem is the first instruction, the 0th instruction, is addition. So when you have nothing written in your memory, you actually add stuff together. So it's, in a sense, this is a brainfuck computer. Which is pretty not good. Brainfuck without conditions, so it's not even Turing complete. Look at that disk before using it. Description. Okay, I have everything at the top. Read bot 1, insert address through data input. 1, clear address. What? 1, clear address. 1, 2, insert. That is the abomination. Okay, that's... It is prettier. Also, you should reset it after welding it. Okay. Probably will be very high up. Yes, it will. Right. God darn it. With the red buttons. Okay. Okay, it was called a ramp. Whoops. Just gonna have a few of those to be able to walk near the buttons. Okay, so the red buttons. Oh my god. Is there so many buttons? What the flip is that? Okay, that's yeah, it have turned on for a second, but then it turned off. Okay, so the computer is, or I guess the thing is certainly interesting. It's prettier. It looks prettier, which is pretty nice. Okay, it's just a ugly debug menu. It's not ugly. I'd say it looks more or less pretty, except the red buttons. Kind of looks weird. So what am I supposed to do? Commands read 1 clear address 1 insert address through input. What these numbers mean? Okay, let's just click something. So this is a... Oh, that's a spot memory. Oh. Oh, right then. The dark blue is address. Okay, this one is address. Green switches is address input. All of them? Okay. Okay, The gate is on means that it can read stuff. That's good to know. And if I'll do that, I have no idea. Look at the Steam page of it. Read 1.1. I uploaded a poor description of what it does. Oh, wait. Oh, okay, I see. Data V. Okay, I'm assuming that's an arrow. Data common. It's even more worse and cluttered. It's even worse and cluttered. Okay, data is that bottom left dark blue. Commons or commands, and the output is at the top. Yes. So this is the data, this is the command. It's even earlier prototype. So let's say no 1. Hell if I knew. Oh. Oh. The binary is reverse. Well, it's fine. Oh. I worked on the reversed one, pane. Okay, well, it did do something. Oh. Jeez, that's very not fast. Why? You set it to move. I did. I think. It's fine, it should be. So let's go to address number... So it's reversed. I also have problems with deciphering how it works. It's fine, let's go to address 2 and write number 6 to it. And let's go to address 1 and write number 9 to it. And let's now... I assume... Let's go to address... Which one was it? This one? And then what if I... What? No, wait. Yeah, long wait. The one is on the left. Yeah, the long wait was to let the printhead move. Okay, I see. Okay, so hmm, 'cause it freaked out when I made it too fast, 'cause bad PC. That's unfortunate. Maybe I'm supposed to. Maybe this. Now, the data and command inputs only work with pre-program instructions. Oh, right, these are instructions. That one is used for to data save. How do I... I'm assuming all of that is reset. Why is there so many reset buttons though? If this is reset. Oh my god, what is happening? The red buttons are for resetting bits and registers. Okay, so you're resetting bit by bit. You see every bit of memory. It's so advanced that I can't even comprehend it. Oh, what? Oh. Oh, right, I forgot. The bits are reversed. Okay, so... What? What is he doing? She's... Okay, it have done... Let's just go to... Address... can I join your world? You can't because I have Fant mod on. I'll try to make it work. It seems to do something. That's very complicated looking memory. First, can you turn this 4-bit Threadripper? Yes, it is. First, can you turn off the raw buttons input? I have no idea what is raw input. Hello, Rat, aka Ethan. This is the compute. This is the thing that Medic sent, or sorry, in the chat. So, raw buttons. I don't know what is what, so I'm just gonna reset everything, and I hope that it will help. I'm as confused as you are. It's fine, it happens. You turned them off, okay. That? Okay. I think I did it right. Now send a 3 into the command. Okay, a 3. Now what? Now give it address and number through data input. That's a not command. That is data input. Give it a address and a number. So this is the address, I'm assuming. And this is the data. Or what is what? This is the data. No, don't use the raw one. Okay. I'm gonna just give it 9. And then I have to input into the same thing. I'm assuming I need to input that. Yes. Okay, now what? Now send one through command. That's more complicated than anything. I think it saved something. It certainly have saved something, but I'm not sure if it's correct because it was supposed to be 6. But it saved not 6. It have saved 7. Actually, no, it's not 7, it's reversed. But it have done something. It have tried to do something. So that counts. That's fine. But yeah, anyway. Ethan, you kind of joined at the right moment because I was thinking of finishing the stream. But yeah, anyway. On that note, we should make a contest on who can decipher it first. I'm sure if we'll just look into it close enough, we'll be able to, or not actually. I mean, how much buttons there is? Like 2 to the power of the amount of buttons, and we can just input random stuff into there and check what will happen each time. What will it output? Although it's not just that simple. It's 2 to the power of amount of buttons. It's probably much harder than that. So we should admit all of the red buttons are for resetting, and the pink ones. The green ones with the green switch are for direct input. So these two, I guess, for direct control. Okay. So this is the comments, this is the data. And so to write something, I have to do 1, then 3, then I have to input some cool fancy data like that. Actually, I'm going to the same address, but that will be a good test. And then let's write something like number 5. Yeah, nah, number 15. Right. I've noticed a small issue, the fact that it doesn't reset what's in the... Yeah, it doesn't clear. Okay, well, I've kind of figured it out. So, that's what those... what the cipher means. 1, 1, 1. Oh, I understand. The thing in the curve... Sorry, in the round brackets is the... So if I will do 1, 1, and input the address, which is 9, and then I will give it a 1 once again, it should, in theory, output me a 1 somewhere. Is this the... And I think it works. So then, if I will want to write something, let's pick address 5 now. And let's pick number, this number. And let's do it. And then let's read it. 1, 1. Go ahead and Wait, which... this address? Wait, wrong address, wait, where did I save it? I have very short memory and also I'm extremely tired. No, that's the... I picked out address 5. Let's pick... oh, wait, I can't. Well, sucks for me. It doesn't reset it. But yeah, that's an incredible computer, kind of. It didn't reset the output. Yeah, I've noticed. So, yeah, this is the 2 of the builds of the medic. The first attempt... oh, sorry. This is the first attempt at something. The memory UI, I'm assuming. With flaws and features. It's fine. And then we have another build, which is the attempted computer, which doesn't compute anything, but it does do at least something. It tries to. Reminds me of my first computer. Yeah. It's interesting attempt. So this doesn't make sound, this does make sound, so this is definitely better than this one. So there is progress, and I'm sure Medic will be able to make a computer if he really wants to. I mean, computers aren't too hard to make if you know what you're doing. If you don't know what you're doing, there is probably tutorials that will appear at some point, maybe even by me. Or Scrap Mechanic may just die, but who knows. But on that note, I will probably finish the stream. I will make another one the next day. I think I may or may not start it at 12 a.m. Moscow time. So yeah, I don't know what time is it for you, but for me it's, I think, GMT plus 3. So yeah. For now, thanks for everyone who watched, which is Medic, Ethan joined at the last few dozen minutes, AXYZ earlier, the first one who joined, and the Burger Box. And yeah, that's it. Thanks everyone, and bye. So yeah.